I'm Tim Ventura from AmericanAntiGravity.com, and we're joined today by James Woodward, Professor Emeritus of History and an Adjunct Professor of Physics at California State University in Fullerton. He's best known for a physics hypothesis proposed in 1990 that predicts a series of physical effects he refers to as Mach effects, but others call the Woodward effect.
Yes.
Let's start out by asking if you could explain Mach's principle for the layperson.
It's complicated to get right. Generally, what it's taken to mean is that the distant matter in the universe somehow causes inertial effects in our local systems. Back in the latter part of the 19th century, Ernst Mach, an Austrian physicist and physiologist, philosopher of science, he's regarded by many as, did a series of critiques of classical physics, and in particular Newtonian mechanics. And it struck him as odd that things that rotate here locally have detectable consequences of their rotation. That is to say, you experience centrifugal forces. And he noted, as others had before him, that such rotations take place with respect to a so-called frame of reference, XYZ Cartesian axes, that are embedded in what he called the fixed stars, what we would call today the distant galaxies. And that suggested to him that there must be some sort of a causal connection between that junk way out there and local effects that are involved in things like rotation. This led his acolyte, at least in his younger years, Albert Einstein, to assume that there really is some relationship between distant matter and local phenomena, inertial phenomena. And of course, there's only one interaction that has significant consequences that acts at that large a distance, and that's gravitation. So the obvious thing to assume, as Einstein did as early as 1911 and 12, is that inertia is a gravitationally induced phenomenon. Mach made this conjecture, and Einstein sharpened it up into the idea that inertial effects are gravitationally induced or inductive gravitational effects. And he was unsuccessful in 1912 in compellingly integrating this into his then theory of gravity, which was still sort of Newtonian. He was working on creating general relativity. But when he created general relativity a few years later, late 1915, he was convinced that he had incorporated the gravitational induction of inertia into general relativity. And within a year or two, he was claiming that what he called then Mach's principle was part of general relativity. The problem with what he called Mach's principle is that it involves something called an action at a distance field theory. That is to say, when you push on your car and it pushes back on you with a Newtonian third law force, okay, that force that it's pushing back on you with is presumably due to the action of the distant matter in the universe. And the question is, how does it know to push back on you at just the instant you push on it, and so on, okay? There are two ways of answering this question. One is a relatively mundane way, which says, well, all that junk out there in the distant universe, which we see looking out our so-called past light cone. That is to say, we see it at an earlier time than now for us. Okay, us instantaneously now is in really distant matter interactions billions of years later than what we see when we look out the past light cone. Anyway, all that junk out on the past light cone, of course, can propagate a field to us in the here and now along that light cone without violating relativity theory and produce a theory in the here and now for us. And it's the action of that field produced by all of that matter out there on the past light cone that is responsible for inertial effects that we experience locally. The problem with this is that it has a few minor defects. To get it really compellingly right, you have to assume that when you push on something, the reason why it pushes back is because it really is interacting with matter out there in the very distant universe, only it's not in the distant past. It's interacting with the matter out there in the distant future. Because when you push on something, you make it wiggle, and the gravitational field that it has wiggles, and that wiggling goes propagating out into the distant future, where it makes all of the matter eventually in the universe wiggle. And the wiggling of all that stuff out there in the future produces wiggles in the gravitational field that propagate backwards in time and arrive here just now in the here and now, right at the right time, to produce the inertial reaction force that you feel. This is a so-called action at a distance version of Mach's principle.
Okay.
Okay, now wait a second. I'm not done yet. A guy named Willem de Sitter, a Dutch physicist who got interested in general relativity when Einstein created it. Remember, this is in the late phases of the World War I and the immediate aftermath of that war. De Sitter got interested in all this, and he pointed out to Einstein that Einstein's field equations had solutions that did not incorporate Mach's principle, the action at a distance version. Okay? And Einstein was ultimately forced to abandon Mach's principle, strictly defined as this action at a distance type of interaction for inertia. The reason why Einstein was willing to give it up was because he was convinced that general relativity still contains a gravitational induction of inertia, that business about the matter on the past light cone producing a field here that produces inertial effects. Okay, that, it turns out, is in fact a part of general relativity theory, notwithstanding that mainstream general relativity has marched away from this steadily for about the last 60 years. It actually is built into general relativity, and indeed a couple of colleagues and I are in the process of working on a paper to be produced at the American Journal of Physics level, that is to say professional physicists but not specialists in general relativity level, and we're going to explain how this is in fact built into general relativity and point out where people went marching off in the wrong direction in the past. Okay, so GR does have this built in. Okay, now what does this have to do with Mach effects? Well, it has to do with Mach effects in the following fairly straightforward way. If you wiggle stuff here locally, okay, what you will find is that you can produce utterly minuscule relativistic effects. You can produce some pretty large relativistic effects if you detonate thermonuclear weapons and stuff like that. But we're not talking about that sort of stuff. If you're trying to propel a spacecraft, Freeman Dyson thought it would be really neat if you could drop atomic bombs out the back and detonate them and ablate stuff off of a shield on the back of your ship, so-called Project Orion back in around 1960. But people don't take seriously that as a realistic way of getting around space-time quickly. If you are limited to what you can do with electromagnetic phenomena and normal matter and the sorts of things that we're relatively commonly familiar with, what you find is that relativistic effects are utterly minuscule. Okay, in other words, say, for example, if you charge or discharge an electrical capacitor, a pair of plates hooked up to a voltage source so that you can turn the voltage up and create an electric field between the plates and turn it down and so on. Okay. You can change the energy in the capacitor by a small amount, and this causes a small change in the mass of the capacitor. The mass change is given by Einstein's famous equation, E equals mc squared. That is to say, m is equal to E, which is some modest number, divided by the square of the speed of light, which is some gigantic number, which means mass fluctuation you can produce is ridiculously small. It's essentially undetectable except in accelerator physics types of situations. It turns out, however, I blundered by accident on some mathematics that had been developed by a guy named George Luchak back in the 1950s, about 30 years ago, a little over 30 years ago. And it turns out that if you have that sort of fluctuation, the E over c squared type fluctuation take place, and if you can couple that to a very large gravitational field, you can significantly amplify the magnitude of the mass fluctuation. Okay? The question is, where do you get a big gravitational field? And the answer is, we live in one. As a matter of fact, everywhere and when in our universe there is an utterly gigantic gravitational field that has a potential energy equal to the square of the speed of light, coincidentally, okay, that we all live in. The reason why when you push on something, it pushes back on you with an equal and opposite force is because you are, in effect, exciting that gigantic gravitational field produced by the most distant matter in the universe. It turns out that in time-dependent circumstances, you can couple that field by just accelerating the object in which your energy is changing, and the gravitational field vastly magnifies the mass fluctuation. Okay, that's the basic physics of Mach effects. Okay, you just take something in which you cause energy to fluctuate back and forth between some small values, you accelerate it in that gigantic gravitational field in just the right way. That magnifies the mass fluctuation, and if you now act on that fluctuating mass with a second force at the frequency of the fluctuation of the mass, you can push on it when it's more massive and pull it back when it's less massive, and in so doing you produce a net force on the system in which you were performing this action on the local system. It's not a free lunch, it requires energy, and it doesn't violate conservation laws because the coupling between that gigantic field and the system that you're working on, you are in effect extracting energy and momentum from the gravitational field due to the distant matter in the universe. Okay, so in a nutshell, that's Mach effects.
That's a lot. Well, now
yes.
let me briefly ask. You'd said it was George Luchak. He was the fellow whose calculation.
Luchak.
Okay, Luchak. And I'll look him up and add him to the story. Now, so I guess I should ask, and I'm jumping around the questions here, but so they're talking about absolute rotation. In Wikipedia, they mentioned that in Mach's principle. It sounds like this is assuming a third frame of reference, a base frame of reference. Is that accurate? And in maybe the distant gravity, you were talking about the accumulation of all of this coming through the Einsteinian light cone. This is kind of a third frame of reference that's independent from everything else.
This is the difference here. Is that what I'm talking about are translational accelerations. That is to say, accelerations in a straight line. When you're talking about rotation, you're talking about a different sort of system, one that is rotating about some well-defined axis and so on. As it turns out, they're ultimately, of course, the same thing because the rotational motion is just a steadily deviated acceleration, okay? And the acceleration relative to the distant matter in the universe is the thing that produces the reaction force. Let me give you an example of what I'm talking about. There's a paper by a fellow named Ken Nordtvedt on gravitomagnetism, published in the 1988 volume of the International Journal of Theoretical Physics, where he talks about gravitomagnetism. He was answering a decadal survey of physics by the National Academy of Sciences, where they claimed nobody had ever observed gravitomagnetism, and he was pointing out that that was not right. If you look at the very last equation in his paper, what you find is he says, and if we have a spherical object with Newtonian potential so-and-so and all that, and it is accelerating with some acceleration A, it drags inertial space with it as some fractional value. Okay, so the question is, to get your absolute space that they're talking about in Wikipedia, what is the value of the coefficient of the acceleration of that sphere that must be the case for the dragging to be complete, so that you don't detect any acceleration of the sphere when it's accelerated. And it turns out that 4 times the Newtonian potential divided by the square of the speed of light is the condition that must be satisfied. That means that the Newtonian potential, colloquially referred to as phi, 4 times phi is equal to c squared, is a condition for gravitational induction of inertia. And that's also true for rotational circumstances too. The rotation in classical mechanics usually gets separated out as a separate term because it involves a mathematical function called the curl of various quantities and so on. And it's separate from the linear effect, which shows up in the equations of motion as a time derivative of something called the vector potential, with a coefficient and so on. So they are different terms. One's a time derivative of the vector potential. The rotational terms involve the curl of the vector potential and stuff.
Well, so let me ask, is there scientific evidence to support Mach's principle? I guess there's a lot of anecdotal evidence, but
push on the nearby object and see if it pushes back.
Well, would the scientific evidence support? I guess what and I'm not asking this question well. I apologize.
Right ahead. Don't worry about it.
Would the scientific evidence support the connection to distant matter, I guess, in the interpretation of Mach's principle? I guess that was kind of what I was asking.
Yeah, let me explain how this all got mucked up back in the 1950s and 60s, right after Einstein's death. Einstein, by the way, insisted that inertia was a gravitational inductive effect. He abandoned Mach's principle in this action at the distance version and fell back to the position of what he called the relativity of inertia. And he believed that to the end of his life. Shortly after the end of his life, in March of 1955, a graduate student at Princeton University, a fellow named Carl Browns, who's a very nice and very sharp guy, by the way. I nominated him for a major prize a year ago, which, alas, he was not the recipient of. But in any event, Carl, as a grad student at Princeton working with Bob Dickey, he was asked by Dickey to look at Mach's principle and the gravitational induction of inertia, which was being debated hotly at the time in the general relativity community, and said, gee, Carl, why don't you see if we can put a theory that had been advanced by Dennis Sciama some years before in vector form into tensor form. So Carl went away and started reading the literature, and Einstein only published technical stuff on Mach's principle once. It was in a series of lectures at Princeton in 1921. It got included in the book called The Meaning of Relativity, and it's included in all the subsequent editions through the last edition and so on. It's about page 100 in that book. There are several pages which are devoted to Machian ideas of inertia and general relativity and so on. And Einstein did a calculation where he claimed that if you bring up local matter in the vicinity of a test object, that local matter will change the gravitational potential energy of that local object, and in so doing, it will change the mass of the object. And that means, in principle, that you should be able to distinguish accelerations from gravitational fields simply by checking the charge to mass ratios of elementary particles. Because if you're in the presence of a gravity field, it changes the mass of the object. But if you're just accelerating in deep outer space, far, far away from all local sources of gravity, there isn't any local gravitational field to change the mass, and you get a different value. Okay, this is a violation of the equivalence principle because it makes it possible to determine whether you're in the presence of gravity or merely accelerating by measuring charge to mass ratios in your small enclosed laboratory. You don't have to go to the window and look out to see whether there's local stuff nearby or you're accelerating in deep outer space. That's a violation. And this, by the way, is correct. Carl's argument is dead on correct. You got it exactly right. Okay? It turns out that general relativity requires that the spectator matter argument lead to a gravitational interaction, if any is present, that does not alter the rest masses of local objects when nearby stuff is piled up beside them. That is to say, turning this around and putting it in slightly different mathematical form, that the total Newtonian potential in general relativity is something that is called a locally measured invariant. That means that it can have different values for different observers in different places at different times, but whenever you make a local measurement of the value of the potential, you always have to get the same number. So when you make a measurement in your laboratory, wherever it is, you always get the same number, meaning you always get the same charge to mass ratio. Okay, the coefficient that involves a Newtonian potential of the acceleration in the equations of motion is 4 phi over c squared, that thing that I was telling you about with Nordtvet's paper. Okay, it turns out that the speed of light in vacuum has exactly the same property as a Newtonian potential. Okay, it's a locally measured invariant too, because the speed of light, no matter who you are, where you are, when you are, or what's around you, when you make a measurement of it, it's always 3 times 10 to the 10th centimeters per second. Okay, even if you're at the horizon of a black hole. Okay, now for a distant observer looking at you measuring light in the vicinity of the horizon of a black hole, he determines that the speed of light where you're measuring it is, if not zero, very close to it. Okay? And of course, you have slowed down in his view too. As you're making your measurements, it takes forever for you to do anything. Okay? That's because the speed of light in vacuum is a locally measured invariant. It's not a constant, as people sloppily call it, because in special relativity, you can treat it as a constant. Okay?
Okay.
All right. Now, what that means is, if Carl's right, the gravitational potential has to be a locally measured invariant. And if it's any value other than zero, and he made an argument for effectively treating the value as zero to make the local laboratory transparent to the effect of external matter, as he put it. Okay, if it's any value other than effectively zero, it has to be equal to 4c squared. Okay, because the coefficient of that term in the equation of motion for translational accelerations has to be 1 in local measurements. Okay?
Okay.
All right. All right. Now, all of this Carl's argument caught on. It led to the creation of something called scalar tensor theory, which is well known in the history of GR, and there are people who still pursue it in different forms for a variety of reasons. It's not something that's gone away. They did a lot of very sophisticated work on it after that. The problem is that the assumption that the Newtonian potential in local laboratories is effectively zero is wrong. It's not zero. It's 4c squared. Or it's 1/4 c squared, so that when you multiply it by the 4, you get c squared over c squared. Okay?
Okay.
All right. Now, that's the reason why all of this is why I and my friends who are working on this are having such a hard time convincing anybody to take it seriously, because they don't believe that the distant matter in the universe has local consequences. They don't believe that inertia really is gravitationally induced, as Einstein insisted was the case. Okay? Problem is, they're all wrong. It is gravitationally induced, and you can take little systems and make the energy in them fluctuate while you're accelerating them, and because of the acceleration added to the fluctuating energy, couples it to that ginormous gravitational field due to distant matter, you can amplify the effect to useful levels. Okay, so where we are at this point is trying to engineer, it's not really a science problem as far as we're concerned anymore, though it may be for others. We're trying to engineer these little gizmos that I invented many years ago and have used to demonstrate that this actually works. We're trying to engineer them to the point where they produce useful levels of thrust for modest inputs of energy and will last long enough to be useful for some reasonable lifetime. And we've got a NASA grant through the National Innovative Advanced Concepts Program. It's a phase 2 grant, which is $500,000 over 2 years. We're looking at finishing it up in a few months, the end of May, and I am literally spending my time trying to engineer these blasted things so that they last long enough to be useful and that they produce enough thrust to be useful at small arrays of devices.
Well, let me jump in really quick.
Sure.
So going back actually dovetails into your device. How do Mach effects work, in your view, for space propulsion?
You take a stack of piezoelectric crystals, okay? Piezoelectric crystals, when you put electrodes between disks of piezoelectric material, the disks plus electrodes act as a capacitor. Okay, so you can drive the stack of crystals with electrodes between them with an applied voltage, and you cause a alternating electric field to appear between the plates of the electrodes in this piezoelectric material. Okay, that causes the energy density to change. That's the energy fluctuation. It turns out piezoelectric crystals, of course, are electromechanical devices, and when you do that, they expand and contract depending upon the sign of the voltage. Okay, so you can take a stack of these things and apply a voltage to them, and you're causing the E over C squared energy fluctuation in the stack, no matter what mechanically they do. But you're also producing the acceleration because of the changing dimensions of the stack due to the electromechanical effect. That causes the accelerations that you need to couple to this gigantic gravitational field due to distant matter. Okay, and if you get everything working right, so that the energy fluctuations taking place at the right time and the mechanical oscillations doing just the right thing at the right time, and it has to be at two frequencies, the first harmonic and the second harmonic, because the second harmonic is what gives you thrust. Okay, you do all that, you make these things wiggle, and what they do is they produce a little bit of thrust. As a matter of fact, when I came in today and ran the latest variant of trying to make these things work better, I managed to get one of these little gizmos to produce something on the order of 20 micronewtons of thrust. That's on the order of an order to 2 orders of magnitude larger than they've been doing in the not too distant past. So if we had a Zoom connection, I could show you a movie of the first run of the day this afternoon, and you could hear me say, "Oh, goddamn," because the acquisition program picked up the overdriving and booted me out of the program and reset it several times before I changed the scales and got it to do a complete run without messing up. Anyway, they're small forces, but 20 micronewtons, let me put it this way. 20 micronewtons is about a factor of 50 below what you need in order to be able to use these to station satellites and change the orbits of satellites and stuff like that. So if you had 50 of these little gizmos producing 20 micronewtons each with a, say, 10% duty cycle or something like that, you'd have something useful that you'd never have to refuel it. All you have to do is provide it with energy from a solar array, and it'll work forever. So anyway, I'm getting far astray. Suffice it to say that the technology, from the practical point of view, is in, I think engineers call it the TRL3 Valley of Death. It's the way it's usually put. That is to say, you've demonstrated the science works reasonably well and all that. And you've got something that looks like it might work, but it's not so convincing that it will actually work that anybody's willing to put a lot of money into it yet. So NASA is putting some money into it, and they're encouraging us to get it to the level so that others will consider putting significant amount of money into it.
Now, speaking of NASA and NIAC in particular, you had sent me a slideshow,
Yes.
And one of the things that you described, you did provide some background about that. You would describe something that you're testing called the Mega Drive. Is that the?
That's this thing. That's just a fancy name for it. A year or two ago, Heidi Fern, who's been working with me since about 2012 on this project, Heidi was involved in a conversation with another member of our team named Jose Rodal, okay? And Jose and Heidi were talking about it, and they were trying to talk through how physically this works. And Jose said, look, what you're dealing with here is you have to put energy into the device to produce the energy fluctuation and cause the acceleration, okay? So you're not talking about a free lunch. You have to activate the thing, and you have to have a source of energy to make it work, and so on and so forth. But you're getting a lot more out of it than what you're putting into it because you're coupling to this gravitational field. It's sort of like in rocketry, you send your rocket around the planet Jupiter or something like that in order to produce a slingshot effect, okay, which is called a gravity assist mechanism, okay, for rocketry. And he said, you can think of it as sort of you're making one of these little gizmos, in effect, be slung around by the entire universe. That is to say, you're getting gravity assist from the distant matter in the universe that produces this gigantic local field. And she said, that's it. We'll call these things Mach effect gravity assist devices. That is to say, the Mega Drive, okay? It's still a Mach effect thruster, which is what I've called it for decades, okay? Same thing, new name, but it sounds cooler.
Well, and so it sounds like this is a newer version of the piezoelectric transducers that you've been working with for
Oh, it's
quite
the
a
same
while.
stuff. It's the same stuff, Tim.
Well, let me ask then, and again, I know you've been working on these for decades at this point.
A long time, yes.
What is it that you've refined about this? I guess what was wrong with the past attempts? I know that you've gotten some results. It's been difficult getting above the noise level, and I guess I'm wondering.
We can get above the noise level easily. That's not the problem. Our problem has been that when others have asked, in particular Martin Tamar and his students at TU Dresden, have asked for equipment to test on their systems, they have not, how should I put it? They have not tested the stuff with real adeptness, and they have been quick to say that there's nothing there. 2 years ago, I sent them a device to be tested, and the stuff that they needed to test it without detailed instructions. And they just ignored all the stuff that I sent with it and went ahead and did it the way they thought it should be done, and they didn't see anything. Okay, then about a little over a year ago, Heidi went out with a couple of devices and some more stuff, and she was there and oversaw them putting it on their equipment and all that, and they tested it, and now they saw the effect. But as soon as she left, they took it off of the vibration isolation we had provided and discovered that without vibration isolation it made their balance vibrate, and they just assumed that everything was just due to vibration in their balance. Okay, so again, they reported a null result. Okay. Martin was here last August 30th, and he told us that they were going to say this at a major meeting in a month or two. And I said, gee, Martin, you just saw our device produce thrust. Let me show you that that's not due to a Newtonian vibrational artifact. Turns out a year earlier, when all of this had first Newtonian artifact prep had started up, we had gone out and bought a Polytech laser interferometer. This is a world-class instrument, okay, that measures vibration to very minute levels and so on. And so Heidi got out the vibrometer and set it up, and we showed him that the vibration in the device vibrates, there's no question about that, okay? But the vibration isolation equipment that we had provided them with, which they had gotten rid of as soon as she left, okay, in our system, isolates the balance from the vibration very, very well. There's no vibration that gets to the balance, and vibration must get to the balance if the vibrational artifact hypothesis is to work, because it has to work as a stick-slip mechanism in the support bearings of the balance beam. Okay, and if no vibration gets there, it's not a vibrational artifact. We demonstrated through him that it wasn't a vibrational artifact. He went away unconvinced. He didn't want to believe that it wasn't a vibrational artifact because they'd already written their paper and sent it in and so on.
So it sounds like you're testing on a calibrated scale with counterbalancing mass points inside of a Faraday cage and with with vibration isolation as well, right?
Yes.
Yeah.
If this were a Zoom call, Tim, I could take my video camera here and I could show you the apparatus. I could actually let you watch a run in progress too, or show you a movie of a run in progress. I could show you the movie of the semi-catastrophic first run of the day this afternoon. Anyway, yes.
Now, is this the same as the Fullerton device? You had mentioned that in the paper.
Yes.
Okay.
Yeah, they're all the same. They're all little stacks of piezoelectric crystals. They are clamped onto a cylindrical brass reaction mass because you have to have something to push against to make a thing oscillate and accelerate. Okay, and then you have a bracket that connects that to the Faraday cage. Okay, and what we're doing right now, as a matter of fact, earlier this afternoon, I took a bunch of drawings over to our machinist to change the mounting bracket in such a way as to produce the vibration getting to the Faraday cage, and at the same time letting the device itself vibrate through larger oscillations, because that's what you want to do. Okay, so we're in the process of engineering technical details to make the things produce more thrust and also reduce unwanted things like making everything else vibrate too.
Yeah. Well, so as this progresses forward, do you have any ideas for making the thrust levels even higher in the future? It sounds like what you're doing now is stacking in series, but as funding potentially increases in the future, are there any bigger, larger directions that you're going with it?
Actually, parallel. We're putting them side by side. We're trying to make each device produce as much thrust as we can get out of them. Given the known system, we're not starting off with, in effect, from scratch with a completely novel design. We're taking what we know works and trying to refine it and make it more stable and robust and all the rest of that, and then putting them in parallel with each other to increase the amount of thrust. Are there other things more dramatic that can be done? Yeah, you can miniaturize these things so that you make gazillions of little itty bitty ones that produce specifically much more thrust than these devices do. Okay? That is to say, what you want to do is you want to create a MEMS project where you get little piezoelectric gizmos on a substrate and all of that with appropriate reaction mass elements and so on, and you have an array of thousands of them that produces significantly more thrust than a similar sized physical array of devices like what we're using, which have PZT stacks that are about 3/4 of an inch in diameter and about 3/4 of an inch long. That's gigantic by comparison with a MEMS system. But nobody's going to invest in trying to develop a MEMS system until they are convinced that what we're producing with these things really is the real deal. Okay? And that is, in fact, what NASA is trying to establish by giving us this grant. They are, in effect, saying, okay, show us. And by the way, we're going to have someone check up on you. They have a fellow at NRL who is being contracted by them to check up on us, okay, which is separate grant, okay, and that's fine. We're going to work with him. We will provide him with whatever he wants or whatever he needs and so on. We'll give him devices and we'll tell him how good his balance has to be and what to look out for and all that. But he will be operating as an independent entity. He will not be formally a part of our grant project. Okay. And he will sometime I'd say the next 6 months to a year, be able to say, yeah, they're looking at the real thing, or no, that's all a lot of garbage. It's a lot of wishful thinking, and you shouldn't pay any attention to it.
So that was all of the questions that I had. But I mean, I'm happy to just kind of shoot from the hip, I guess.
Sure.
One thing I was wondering, you're talking about rotation, right? Mach's principle is talking about rotation and vibration and gravitational coupling. Do you think that this may relate in any way to, like I've heard about precession, how if you tap a spinning object, the precession takes that force 90 degrees off, right? Do you think it might be related to that in any way?
Our precession and nutation and all of that stuff and rotational mechanics, they are all well understood, normal mechanical effects. There's nothing mysterious about them. Yes, they are related to that because all rotational effects are, in effect, Machian effects. Centrifugal forces, which in elementary physics are often called fictitious forces, which don't really exist. That's nonsense. They are quite real forces. Okay, they are in fact the Machian gravitationally induced forces in a system that's undergoing rotation. As I said, a rotational system is a special system because the equivalent of Newton's first law of motion, body at rest stays at rest, or uniform motion in a straight line, inertial motion. The equivalent for a rotational system is that an object spinning with a given angular velocity in the absence of any external torques continues to spin with that angular velocity. Okay, and the reason why that happens, of course, is because all of the parts of the body that's spinning are being constantly accelerated towards the axis of rotation, but the velocity of each of those mass elements in the body is perpendicular to the acceleration. So the change in the velocity as the thing rotates that shows up as an acceleration merely changes the direction of the velocity. It doesn't do anything else. Okay? It doesn't speed it up. It doesn't make it spin faster or slower. Okay? Now, if you take that as your basic understanding, and then, of course, reduced to that level, it's elementary and obvious, it turns out that all of the other seemingly mysterious effects like precession and nutation and stuff like that, they are not mysterious at all. It's just that they are vector mechanics as opposed to scalar mechanics. They involve forces acting along different lines and stuff like that. And so people view them as mysterious. They're not mysterious. They're just a consequence of the mathematics being a little more complicated than what we're normally used to dealing with, which is simple linear systems.
Oh, now you're working on this with NIAC 2, if I understand right?
It's a phase 2 NIAC grant, yes.
Oh, okay. I wasn't sure if NIAC was if they were still around. That was why I was a little surprised.
Yeah. Oh, yes. Yeah, no, NASA's still around, and NASA's putting money into this. They want to find out whether or not this really works. And as I understand it, the budget has recently been passed, and while there were some cuts proposed and this, that, and the other thing, NASA, and in particular NIAC, was not on the list for getting chopped.
Oh, wonderful. Yeah, I know they have a lot of projects they're doing, and they're scaling up with SLS and all the other stuff as well. So, yeah. Well, Jim, I think that was everything I had for today. Is there anything that you'd like to add?
Wish us luck.
Okay.